is that they're pretty much trying to do the same thing, which is they're trying to improve the quality of the retrieval. Right? So I'll give you an example. So this is a baseline for retrieval that a lot of companies use. This is sort of like the default. And this is called HIDE, which stands for Hypothetical Document Embedding. And the idea is very simple, that instead of searching directly the query, you basically ask an LLM to generate a dummy answer with this hypothesis that that dummy answer, the hypothetical document, lives closer to the real answer in the embedding space of the model rather than the question. So on the right, you can see what the hypothesis is. And it seems like a very simple trick to improve retrieval, but it has been found that in most benchmarks, this performs pretty well. And it also makes sense because most of retrieval happens, like commonly in the Gen AI era, it happens using semantic search, and semantically, a dummy answer lives pretty much close to the real answer, right? So this is the idea behind HIDE. But from a bird's eye view, if you step back, this this name loaded with a lot of jargon, hypothetical document embedding, HIDE, it's pretty much a simple idea that in order for your RAG to be performing well, you need to have good retrieval quality, right? Okay, let's look at one more. We'll not look at all 25, but just to give you an idea. This is sort of called a corrective RAG, or you can also call it query rewriting. So what this does is it takes the query, performs retrieval, and then uses some judge. Maybe it's some deterministic algorithm you wrote, or it's just LLM as a judge. It pretty much is an independent judge. And then it judges if the quality of this retrieval is actually relevant to the question that you asked, or the query that you asked. If it's not, then you sort of transform the query by performing, adding context. That can be through an independent node in an agent, or whatever other methods you want to add context to it, and then it performs the same retrieval again. Or then moves on to generation. Now, again, the same sort of principle applies here. You're pretty much trying to improve the retrieved context, right? You're pretty much working in that same area of contextual retrieval. Okay. And you can look at all the other kinds of RAGs, graph RAG, corrective RAG, or I don't know, whatever kinds of RAG that you have. The core idea will remain the same. And so one of the things that sort of becomes clear with this exercise is that these are not deep tech breakthroughs. This is something that you could have thought of while struggling with retrieval quality problem, right? So the core idea that comes out of this is that RAG is only as good as the retriever. So when we talk about RAG, it stands for Retrieval-Augmented Generation, where the idea is that you improve, or you sort of ground the LLM to prevent it from hallucinating by providing it necessary and sufficient context from which it is supposed to answer a given query, right? So you're pretty much saying that, hey, only use the query that I provide to answer my question and nothing else. And so that way you are sort of providing some guardrails to this LLM so that it does not hallucinate into oblivion. So now, if that's the case, it sort of makes sense that it's going to be only as good as a retrieval, because it's retrieval quality, because it's going to always answer questions from that. Okay. So it is this not to say that you should never think of the generator. It is also important, but it is important only in a sense that you provide your answers some relevant vocabulary, not exactly the right, not exactly technically you're not technically improving correctness of a response, but maybe you provide some vocabulary to your generator by fine-tuning the LLMs, but it's not really related to the quality of answers you generate, right? Okay, so now once we've settled this, how do you actually go about improving the retrieval performance and systematically? Now, why this matters a lot is you could do a bunch of things, right? You could just experiment with any random thing, but by improving systematically, I mean that if you repeat these same steps in different problem situations or different real world situations, you should pretty much expect similar results in different um, ratios, obviously, but similar results, right? Okay, so the first thing that you should try when you're improving retrieval performance is try advanced retrieval methods. So this could be lexical search, right? Like by default, all the RAG systems use these days, right? In Gen AI era, everybody uses a vector search. You could do that. But in some cases, you might find, and I'll discuss this in more detail when exactly, but in some cases, you will find that, full text search, BM25, keyword search performs much better. You could use that, or you can combine them both using hybrid search techniques, sparse and dense. That's one way. Then comes re-ranking. There are special class of models that actually take the retrieved results and then further re-rank it. Now, I'll talk about why that is also useful. And then fine-tuning your embedding models, like that's the crux of how semantic search works. So you could also fine-tune that on your data. And then I've crossed out, trying different chunking techniques. These are getting famous, things like late chunking, semantic chunking, and then before that, there's like probably 10 chunking methods. Why I've crossed this out is not because it might not improve your, or it does not improve your retrieval performance at all. I've crossed this out because it's not guaranteed to. So there's a lot of studies on this as well. Uh, a very good one is by ChromaDB. If you search for, chunking techniques, ChromaDB, you will get a study on that. I even read that. I talked to the guy who did it. And the idea was there is some movement, but there is no such chunking technique that performs best across the board. So if you choose something, like if you choose a sentence splitter, or a recursive text splitter, you will see some difference, obviously, but you cannot say which one is better because there's no performance improvement across the board in that benchmark. Like the one data set might perform better on a specific kind of chunking technique. So the idea is that movement is not by much. So you just use the best default chunker, which is maybe a recursive text splitter. Now, there is one chunking technique that performs the best across the board that is called semantic chunking. And the idea with semantic chunking is that you don't have a deterministic algorithm that performs chunking. You basically take a paragraph of text and pass it to an LLM and say, hey, based on your understanding of the language, chunk this into most semantically grouped chunks. And that works really well across the board. But why I've written don't use it or use sparingly is because it's very slow and it's not non-deterministic. You're pretty much using an LLM to sort of chunk the text. You can do it if you have all the compute in the world, but it's a slow process. And when you re-ingest data, this becomes a bottleneck. So you can try it, but not recommend it. Same way, late chunking as well. Now I've linked, you'll get these slides. So I've linked the detailed studies that I did on all of these techniques, but I'll cover the findings and the tips and tricks from all of these in this talk, so that you don't have to read it from end to end. Okay, moving on. Just for demonstration purpose, I'll just show you where all of these techniques sit in this retrieval pipeline. So when you chunk your text, the first thing that you do is generate the embeddings. So if you fine tune the embedding model, this is where it sits. You have to re-ingest your data with the new model. And when you move towards the right, you'll see that hybrid search or re-ranking sits after the ingestion has happened, or maybe I should say towards the retrieval part. So when you're working with hybrid search or re-ranking or fine-tuning re-rankers and things like that, you don't really need to re-ingest your data. So I call this, or anything that sort of does not require you to sort of disrupt your pipeline completely, I call them lower hanging fruits comparatively, right? So this is why I've put hybrid search at the top. You should try it because it does not take much from your side, right? You don't have to uh, re-ingest your data. You don't have to train something. You can just change the query type, see if it's working. If it's not, just go back to what you were using, right? So that's the idea. This just puts things in perspective. Okay, moving on. This is pretty much how you can perform hybrid search when you're using LanceDB. You don't have to do anything, just specify the query type equals hybrid, and we do all the uh, you know uh, the calculations and all of those things in the background. Now, the story behind this graphic is that when I was experimenting, when I was building this feature, or we were building this feature into LanceDB, this hybrid search feature, we were not sure if this actually was this kind of like this important feature. So we ran some tests on um, standard data sets on Llama Index. And this is what we found out. So on the left and right, you see two different experiments. These are small data sets, but still real world data sets. So on the left, you see Uber SEC filing dataset. On the right, you see Llama 2 paper dataset. You can find these on Llama Index today. Maybe not. I'm not sure. This is probably more than a year old. And what I did was I pretty much ran the retrieval quality, hit rate, or recall test for different query types. So one is vector, one is full text search or BM25, then re-ranked vector, re-ranked full text search, and hybrid. And as you can see, in some cases, FTS, full text search, performs better than vector search. In fact, in both of them, and hybrid search performs the best. Now, this is what I said before, that you should always test this out. What happens is, in some cases, it really depends on your data set. So if you look at Uber dataset, Uber SEC filing dataset, the prompts and the contexts, or the query and the context, are very keyword oriented. So SEC filing is pretty much like a financial disclosure of a quarter or something like that. And what you're supposed, the question, as a company, you're supposed to talk about your financials, what worked, what didn't work, and things like that. And the prompts, the queries were very keyword oriented. So it could ask something like, how much profit did Uber make in this quarter? And based on that, it's pretty much natural for full text search to perform much better, because the context is very short, and the prompt and context are very keyword oriented. So matching keywords will give you good results. So it works better than that. But what happens is, if either of the two things happen, the data set is too big, or the context is too big. So what happens is, when the context becomes big, uh, um, it becomes more difficult for it to match using keywords. Then semantics matter more, right? So if you were to match a poem or a prose or an artistic description of something that is not keyword oriented, you will pretty much always fail with keyword. You want to go with meaning. So the trick is, whenever there is meaning, uh, primarily, or that, or meaning is the primary sort of key for searching, you should use vector search. If not, then full text search. But how do you know? Just run some evals, right? That's the idea. And so when we saw, okay, this is really just by changing different types of um, just by switching different to different advanced retrieval techniques, you can get good results. This is what we built, and you can try LanceDB hybrid search with just one line of change, nothing more, right? So this is the first technique. How hybrid search works is, it takes sparse representations, which is full text search, and then dense, which is vector search, combines them together and gives you, and then sort of re-ranks them using some sort of a re-ranker. By default, we use reciprocal rank fusion, which is just a very simple algorithm to take two sets of results and then combine them and rank them. But you can use your custom re-rankers as well, which I'll come to next. Re-ranking again. So re-ranking, pretty simple to use with LanceDB. Just search write a search query, and then towards the end, put dot re-ranker and pass in your re-ranker. When we built this re-ranker, it was not as famous. Now a lot of companies have their own re-rankers. Back then, Cohere was the best. Now I think a lot of open source re-rankers even come close to or beat Cohere's re-ranker. But before we get into the nitty-gritty details of the re-rankers, I would like to talk about why they're important. So this is on the left, you will see a representation of what really happens in retrieval process. So you search for something, you get some candidate results, which is the raw retrieval results. And then that is something that you put into or feed into an LLM, right? But what reranker does, it sort of sits between that process and it tries to make sure that the best context is at the top, right? Now, why, like you might ask that if the model pretty much sees the same context, why is it important to actually re-rank? And the answer is, even if the model has a lot of context, it does not matter. I think a lot of you might have seen those memes on the internet where they say that model claims to have 1 million token window or context length, but beyond 200K, it sort of starts to uh, perform bad, right? Uh, uh, so this is what happens, right? Even if you have a lot of context, you really want top results to be most relevant, right? So you still want to improve relevance. Uh, and and also, not all retrievers are meant for RAG. You can use it for something else as well. You can use it to build recommender systems, and in recommender systems, you obviously always want the best results to be at the top. So re-ranking is useful then as well. So you could use built-in re-rankers, but the thing is, as you work with domain-specific data, so for example, you are, let's say, a biomedical company, a financial institution, your data becomes specialized over time, right? So you're not dealing with a normal distribution, you're just dealing with very specific kinds of data. And so the generally ranking performance, although it gives you some boost, it might not, you might not be extracting every last drop of performance. So what you could do is you could fine tune or train your own re-ranker. And the good thing about this is that a lot of the learnings that you take from here applies on, uh, excuse me, on fine tuning embedding models as well, right? So I'll just move to that in a bit. And this next segment, I think, is most interesting for people who are interested in fine tuning, training their custom re-ranker or embedding architectures. So, okay, hold on. I'm not sure what I did. Oh, I'm seeing my Zoom window. One second. Okay. How do I minimize this? Uh, okay. It's right here. Cool. Okay, so I'll go through some common re-ranker architectures. Um, you see on the left side first, there are two architectures listed there. Bi-encoder and cross-encoder. And bi-encoder is nothing but embedding models, right? The idea is, what is an embedding model? Embedding model takes any sort of object, it's text, image, these days even videos with VJEPA kind of innovations. But the idea is it takes any object and represents it in vector form. Um, the 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 name bi-encoder means that if you're looking at two sentences independently, what embedding model does is it encodes them independently. It does not care about what came before or what comes after. That's what bi-encoder. But when we talk about cross-encoder, right? This is the most common re-ranker architecture, by the way. So what cross-encoder does is it encodes both of the sentences, or in this case, sentences, you can think of it as objects together. And so instead of giving you one embedding representation, it directly gives you a score, similarity score, or classification score. Because why do like if it's seeing both of them in pairs, what's the need for embedding models? Because you will always perform dot product to get the similarity. It just gives you similarity, right? That's the idea. So on the right side, you will see how this architecture actually works. So you see query, and this is, by the way, a simplified version. There is interaction at every stage. So both query and documents are embedded together. And so they see each other in each stage. They're accessible to each other. And finally, they give out one score. And that score is the similarity score. Okay. The other, and by the way, the thing is, let me spend some more time here. It's really important. You could say that cross-encoder is so much more powerful, and obviously is. Why use it as a re-ranker? Why not just use it as an embedding model? And the answer is because you cannot store embeddings offline. It sees everything in pairs. So how you actually run this is you have a query, and then you take that query and all the possible contexts, which could be even in millions. So what you do is you create all that query context pair. So query one, query, and then context one, query context two, query context three, and to n, and then you have to perform this. And this is super slow because it works in pairs. You cannot know query ahead of time, and that's why we use embedding, because embedding, you can store all the context embedding together and perform, uh, create vector indices, all of that, and then towards the end you can just search. Now that's why combining them together works really well. So you perform vector search and get uh, top 20 results quickly. And then what you do with cross encoder is now you have narrowed down your search space from millions to just 20, and then you can run cross encoder on just 20 of those. And what happens is if the context is there in that 20, like top K, it comes at the top, or it's expected to come at the top. That's the idea. Okay. But in the recent times, we have a more innovative architecture that sort of sits between the two, right? Um, and so it works in two stages. So in the first stage, it supports offline indexing, so you can still create vector representations of your documents, and what you can do is you can save that in the vector database or whatever kind of indexer you're using. And during the query time, you get you encode the query and then you make them interact. So in the previous cross encoder, what I told you was that it did both the query and document interact throughout the process. And in late interaction or contextualized late interaction, but it's pretty much done the same way, but they don't see both of them don't interact early on. They interact towards the end with this maxim operation. So towards the right, you will see how this happens. We first encode them independently as tokens, and then those tokens get interacted together, and then you get this final score, which is the similarity score, right? So it sort of sits between the two. Because it sits between the two, it is used both as an embedding model and as a re-ranker. So Colbert architecture is really very famous these days. It's one of the most hot topics in both in production as well as research, because people are now trying to, because it's so powerful, it performs really well. People are not trying to make them production ready at scale. Obviously, it's so powerful, but it's also compute intensive, so you cannot use it for tens of millions or billions of vectors. But if you sort of the going ongoing R&D in this area sort of tries to push it in that direction. Okay, so this is what re-ranker is, right? This is what it does. Now, how do you actually go about training a re-ranker? So I ran some experiments on both re-rankers and embedding models, and I took a data set called Google QA, or for short, GooQA. Um, it had 3 million rows. I took 2 million for training, and then some subset of that remaining 1 million for testing. And the process for training uh, a re-ranker model or a ranker model and an embedding model is pretty much the same, right? Except for the loss function. And so what you do when you're training a re-ranker model is you have to incentivize it to put the right context at the top of the list, right? So the first step would be you need to make the training data really uh, difficult for it to uh, in order to train a robust re-ranking model. So the first step is the most crucial one. Beyond that, you can use any script that you like. The first step is to mine hard negatives. What I mean by mining hard negatives is that, for example, Well, first I'll just give you what mining hard negatives means. So there are negatives. So let's say there's a query. What is the capital of this particular country, right? And its context obviously should be, or something that should be ranked at the top should be the right answer. This particular city is, or state is the capital of this country. But there are other simpler negatives, right? Any random sentence you choose, any random context from the data set you can choose, that would be a negative. So you could choose like dog has four legs. That's a negative context. You can choose any. The thing is, you train good re-ranker models by choosing hard negatives. So what a hard negative is it really lies very close, or it is very similar to the positive, but it is actually negative. So it would be like if you're talking about um, uh, a city, so it could say the positive could be like, this particular city is the capital of the state. The negative could be this particular city is not a capital of the state, but semantically they are similar, and you can think of n such answers in the data set. So the negative has to be really hard for the model to determine, and hard negative means that it is the wrong answer, but it sits very close, or it sounds very similar semantically to the right answer. So how do you do that? You do that by using an independent embedding model, right? So you go through a data set. You already know what the right answer is because the data set it's a supervised process. You have an input and the output. But to find the hard negatives, you just run a semantic search through an independent model that you're not training, so that you don't pollute the data. And what you do is you just, from that corpus, you find top n hard negatives, and that's how you build the data set. And this is what mining hard negatives mean. Once you do that, it's pretty much simple. Then you just do cross entropy loss, and then use all of your favorite evaluators. Like BR is the retrieval benchmark. You can use something custom. You can use cross encoder re-ranking loss, all of that. And then finally you get some trained model. Now, this process is pretty much the same for embedding models as well. You just use a different output format. You just have one negative instead of five, because you're not training it for re-ranking, you're training it for representation. But that's it. The code for this and reproducible logs and everything is again listed in the study that I've linked in the first few slides. So you can read this. I've went into detail in the blog about each step and some examples as well. If you're interested in training and tuning, you can go there. But now I'll move on to the actual results that I saw. Okay, so I used that data set to train, and then from the remaining 1 million, as I told, that the data set consisted of 3 million. I only used 2 million for training. From the remaining 1 million, what I did was I took 100,000 uh, samples, and then from that 100,000 samples, we took 2,000 for uh, evaluating hit rate. So by the way, this is actually a difficult data set now, because you just have 2,000 queries and you have 100,000 sort of possibilities. So it is even larger than some of the uh, test sets available online, right? So it's pretty hard problem. Okay, the baselines. So at baselines, I use MiniLM, a very small model, uh, and both at the rate 10 and at the rate 5 means like, top k. So top 5 means like I retrieve top 5 candidates. And what's the hit rate for that? Or you can say it's recall. So how many so let's say from 2000, how many hits I'm getting at when I'm fetching only top 5k. So it's like 48.75%. At top 10, obviously we're increasing the number of hits that we sorry, the number of retrieved documents that we get at every step. So it goes up. So this is the baseline. And below here, you will see some, junk results. Why? Because these are base models. And that's what we'll do. We'll train the base models. These are not re-ranker models. These are just base encoders. These are not meant for re-ranking. So this is what it proves. You just get 4%, 10%, which is really bad. So now we'll see if we can train them to be re-rankers. And then we will also fine-tune them just to show that this training process works. Right. Okay. You don't have to remember this. This is just all the experiments I ran. These are all trained on a few H100s. And the naming convention goes something like this. The re-ranker architecture. So as I said, those were the base models. So what you do with base models, you attach a head of whatever kind. So that's the re-ranker architecture. The base architecture that I showed you, the number of negatives that I mined. So you remember we mined some negatives, in this case, anywhere between 1 to 5, and then number of epochs I trained for. You don't have to remember this, but this is just the way to read it, just the nomenclature. Now, I trained both the architectures, late interaction, Colbert, as well as the original OG cross encoder. So that's why you see some of them with Colbert, some of them with cross encoder. Now, in this, you will see on the left hand side, if you look at any of these charts, like whether vector search at 5 FTS or hybrid, you will see that we went up from 48 to 60%, right? Hit rate, or 61, sorry, not even that, 61. And still with FTS also the same story, we saw a significant jump, and obviously hybrid search is just an amalgamation of both of those, so we still see the jump and it performs the best. And the same story with at top K of 10, from 60 we went to 68, or yeah, something like that. So this is the idea, that yes, you can train your own re-ranker models. And these, if you look at this is not a lot of work, right? It's just 5 epochs. It's not that much. So maybe an hour or two, at, depending on the model size, obviously. But yeah, it's not too much work. You can do that for your domain specific data. Okay. Results in a nutshell is that, we saw up to 12% improvement, from 48 to 60 something, 61. And then at top 5 and at top K, obviously we are closer to decent results, so that the margin will be smaller, of improvement. FTS also saw improvements up to 20%, but not as, like some of them obviously overfit towards the end. As you can see, the highest epoch does not necessarily mean the best performance, because obviously models do overfit, and this data already is very generalized data, so it's not a domain specific data, so it is more prone to overfitting. Okay, that's on re-ranking. But you don't have to like train re-rankers from scratch. You can also pick up existing, like off-the-shelf re-rankers and fine-tune them using the same process. I just trained from scratch to demonstrate that those hard hard negative mining works. But we could also use dedicated re-rankers. For example, I'm using here, I took Colbert, again, a late interaction model by Answer.ai. That's Jeremy Howard's company. They do a lot of interesting stuff. And so those base performance was already, pretty good. So we got 59% instead of 48 at top 5, and 68 instead of 60 at top 10. And then we further fine-tuned them using the same script, and then it goes up to 62 and 70%. So there's always room to squeeze out a little bit more performance, right? So now our next best is something like this. But what happens if we then don't stop here and then also perform the same particular process of fine tuning with embedding model? So you took the embedding model. That's the last of 3 methods of going about improving your results systematically. So you saw, if you're just starting out, just do what's the easiest. Change the query types and see if something moves. You'll see some signal there. Like if you change query types, there very rarely you will see no difference. You will see some signals there, and then you're like, okay, I've tuned my search type enough. Let's look at re-ranking. So you can use off-the-shelf re-rankers. It's fine, because re-rankers, again, it does not disrupt your pipeline, so you can use it. If you don't like it, just throw it away. Who cares, right? And then okay, you're like, okay, re-rankers work. Now, is it the best re-ranker for my job? Can I fine tune it? And you're like, okay, I'll fine tune it. You fine tuned it. Okay. Uh, and by the way, yeah, so you fine tune, and towards after that, like you get this performance. And just to sort of put things in perspective, because you're adding one more step, right? Like you retrieve something and then you re-rank it before sending to the or the generator or to the user. There will be some latency. Let's look at that as well. So the trade-off, because no free lunch, you have to pay some trade-off. You will see the trade-off is not that much. For this, I'm using T4 GPU. It's the cheapest, most readily accessible. You could even use a CPU, or you can use a much more powerful GPU. The latency is really much lower. You will see the best performing model, Answer.ai here, that gives very low latency. Like it adds very less latency. So your baseline was left 28, or maybe if you add or remove some numerical instability, so maybe plus minus 10. It does not add too much, and the slowdown factor is not that much, like 1.5. Well, that's fine. Like this is just milliseconds, right? Like 100 milliseconds does not really matter to most use cases. It's fine. Sometimes even network round trip takes more than that. So you know, but if it is too much for you, and I address this point here, when you should not use re-rankers. Why do I say when you should not use re-rankers? Because re-rankers is such a no-brainer that everyone by default should use them. Instead of saying who should use re-rankers, I'd probably like to say who should not use re-rankers. And what I say is that it will add some latency. That latency is very small, yes, but it is something. So if your use case is, you're working on that edge use case that even 10 milliseconds is too much for you, don't go for re-rankers, right? You can skip that out. And if your goal is to always be less than a certain sort of latency, then yeah, don't use a re-ranker. But yeah, up until now, we've studied, taken a look at hybrid search and re-rankers. The next is embedding fine-tuning, right? You can also fine-tune embeddings. And again, I'm not going to go into the details of like what the steps are, because the steps are pretty much the same as we discussed. You mine hard negatives. Instead of negatives, you mine one, because you're not ranking, you're just learning representations. So that is enough. And with LanceDB, what you can do is you can simply choose any of the tuned models, something like this, and it will automatically pick it up and start using that for ingestion and query. So this experiment again demonstrated that sort of that training strategy of choosing hard negative works. So again, remember we started off the baseline at 48%. With re-ranking, we went up to 60 with fine tuning for like 1 or 2 epochs, just 1 or 2 epochs, not more than that. You can get to 58. Uh, uh, I mean, with 1 or 2 epochs, you can start to see the improvements. You see from 49, you start to see the improvements, and it goes up to that. And then in the top 10, you can see like 70% from 50 to 70, like 10% increase. And again, this is something that does overfit, right? If you look at the left side, what happens is that the best performing model is not the highest epoch. So you have to be careful to not overdo it. But this is just for demonstration purpose, so it's fine, right? Now, the only difference is that when you are dealing with the embedding models, now if I have to run any experiment, I have to re-ingest my data. Right? I cannot go on working with the same pipe. And that's why you should do it at the last. Like, a lot of times people suggest that you should do it as the first step, just fine tune your embedding model on a synthetic data. I'll come to that synthetic data part, but you should not just blindly fine tune, because it is disruptive to your pipeline. And what if you had a very large model, and then you have large you have large data sets, so maybe tens of millions or maybe more, then you waste a lot of time, compute, resources to just keep on ingesting and reingesting, to try everything, and towards the end, try embedding fine. All right, so what if we combine them, like the best embedding model and the best tuned re-ranker? Can we still improve something? So from 48, if I choose the best re-ranker model, I get this result on the second row. And then if I combine it with the best re-ranker model, I can squeeze out some more performance. So yes, you can combine both, and you should combine both if you're experimenting with that part as well. So that pretty much is like improving stuff. But I will come to synthetic data, because it is very popular and as a topic. So I'll come to that. Now, you should not always fine tune your embedding models. If you decide to fine tune your embedding model, it should look something like this. The situation should look something like this. Right? What I mean by that is that most times when we are dealing with the standard official embedding models, like, I don't know, closed source or even open source, those models are trained on large corpus of data. Right? So it already knows a lot. but it is general in nature. Like, it's not domain specific. So if there are a few queries about medicine or a few queries about finance or general science, things like that, but it's not tuned for any particular domain. So what happens is, if you're just fine tuning for fine tuning sake and your data is not specialized, you will end up in a situation that's towards left. You're pretty much trying to train on the data set that the model is already seeing. A good example of that, and I covered this in detail with benchmarks in the retrieve, like the study that I've linked before. So you might have all have heard of a very common data set called SQUAD dataset, Stanford question and answer, I believe. So that is like, that lies towards the left, that situation, because SQUAD is a part of general standard training corpuses for embedding models, right? So yeah, so if you're training on that, you will see it starts to overfit really quickly because the model is already seeing it. It's not learning something new, and it's just sort of after a couple of epochs, it just the graphs looks really weird. What you want is an ideal scenario when you decide, okay, now my data set has become domain specific. So towards the left, maybe it has some overlap with the large corpus of general data, but you'd like to sort of be in the second scenario where you have first of all large data set, not small, because it again tends to overfit, and you have domain specific data set, not just general data set. And so then it's the right choice to fine tune something. So it's like a rule of thumb kind of thing. And again, you have to look at your data, you have to run some evals, you have to uh, constantly dig deep into your data set to understand what's happening, but you have to be careful about this. So you should just not fine tune all the time. Okay, now what about synthetic data? Can't we just generate synthetic data if I don't have enough data? Yes and no, right? It's more complicated than that. LLMs hallucinate a lot. So what you do with synthetic data generation is you pass some context to an LLM and then you say, ask a few questions about this, and then you use those questions as queries, and then you build a query context data set. The thing is, LLMs ask a lot of weird questions as well. And it has been found like up to like, I think this was in GPT 4.1. When generating synthetic data, LLMs can hallucinate up to 70%. I don't exactly remember the source, like the exact study that said that, but it is really uh, it's a big problem, right? So the quality of a data can be bad if you're using synthetic data, and then you use it to fine tune. It's again not going to bear any fruits. So be careful with synthetic data. Bad data will lead to bad synthetic data. So you need high quality data, and then you need some sort of evaluation techniques to make sure the hallucination is handled well, and then maybe you can do that. So it's not that simple. You cannot just throw anything into synthetic data generation pipeline and then expect that to give you good models. So that's like a caution that I would like to add in this fine tuning section. Cool. So this is how you go about improving a retrieval system, and in turn improving everything that is built on the retrieval system, whether it's RAG or a recommender system or anything else. Okay, now coming to the second part of this, where we talk about building flexible retrievers. So nowadays, we're dealing with multimodal data. And when we talk about multimodal data, there's a lot of ways to represent a data. So we've seen how if you already have a retriever, you can improve it. But wouldn't it be nice if you, from the get-go, build good features so that your retriever is very flexible as the time goes on, right? So how do you do that? So one idea is there are multiple ways to represent an object. So let's say if you're building, as mentioned here, if you're building an online clothing store, there are so many ways to represent a clothing item. Right? You can use its texture, brand, fabric, occasion, like what was it's for, maybe it's business casuals or party wear or something like that, or what it goes well with, right? So you might see, to buy ties or watches or socks or whatever, like it goes well with a particular kind of a clothing item. So there are so many ways to represent that particular object. Okay, that's 1 point. Now, while point one is true. It sort of is also true that user intent cannot be known ahead of time. So if you're building this tool, you don't know what users will search for. So at a particular time, let's say during a festive season, they will obviously search for specific kinds of uh, items, but they might search based on what they already have. So someone might search for say a specific kind of uh, shoes or something like that based on what they already have, or then maybe in some other part of the year someone might just search using brand names or things like that. The user intent cannot be known ahead of time, which sort of makes point one even more important. You need to be prepared to represent objects in different uh, representations. But what again is true that if you enrich your queries, what you can do is you can match the user intent as it comes, because you don't know it ahead of time, with a particular kind of feature, right? So if I already have them represented, I can enrich my user query to match uh, which representation I should use. Okay. Now, smart feature extraction can be used for pre and post filtering or re-ranking. What this means is that if you if there's a user query, you can pretty much use a part of that query or write keywords from that query to extract some things, right? Some important things that can be used for filtering out something for that specific user. Okay, so these are the few things that you can do to build more flexible retrievers. Now I'll show you a quick example that does everything, like implements everything and does it in action. So here's the problem statement. Now in Gen AI era, there's a lot of generated uh, graphics, illustrations, artworks, even. Um, so in this day and age, it becomes really important to know what's real and what's not. So what if you were someone interested in, you're interested in artists, artworks, and so on, and history of art, and you decided to maybe build an application that recommends real artwork to you, like real artwork, like from the history of humanity, and it does it based on, like, it does not really expect you to provide query of a certain kind. So you can maybe search using a poem or a prose, like you can describe that in an artistic fashion. You know how people describe artworks, like obviously they don't describe it literally, like what's in the image. They just sort of provide the kind of mood sort of that it, or the emotion it evokes in them, and then you can search using that. But you can also search literally. Like you could say, I want to see this specific painting by Van Gogh or something like that. Or you could maybe you came across a specific sort of synthetically generated artwork, and then you're like, oh, I've seen this somewhere, or maybe I want to see if something like this actually exists in real life. You can search by image also. So there's different ways of searching it, right? So let's build that application and let's see how these principles apply there. So what we have first is representation. So we get an artwork, and now and now think of how many ways you can represent it, right? You can have its literal description, what it describes literally. Like you can say there's a pathway across the fields, uh, and you can see a house or something like that across painting. There's an artistic description. Now I don't know what an artist would say, what kind of mood it evokes, but generally something artistic, a prose. You could talk about color profile, right? Like it's bright colors, or it's sort of what kind of mood it evokes. Um, it's dull, bright, depressing, or sort of uplifting, things like that. And then image features. By image features, I mean pixel level features. For that, you will use embedding models, clip, siglip, something like that, whatever works well. And maybe description features as well. So the description can also be encoded as a vector. You can use that as well, right? And like this, you can go on building features, maybe a lot of them. And I think you should do it as many as you can, because you never know which one is most relevant. But it's easy to get lost, right? If you have, let's say, 10, 20 features, how do you know which one to choose? So the idea is, let's use LLMs as semantic routers here. So a user query comes in, and you can use LLM as a classifier to classify which feature matches best with the user intention. Again, you can specify keywords as well. This is an idea. Now, this is a POC kind of thing, so we can use LLM as a classifier. I'll just give you a word of caution here. LLMs are non-deterministic um, by design. So beyond a certain number of features, they might start to perform bad. So if your number of features increases over time, you can think of fine tuning an LLM or training your own classifier. This is how routers are treated or built by your favorite LLMs as well. Like they route to different agents. But yeah, for smaller number of features, it works really well. So you route it. So it's like a very simple idea of using LLM as semantic router. So you don't have to build logic around what to use, what to choose, and things like that. Okay. So with LanceDB, we make this really simple as well. We have an offering called Geneva. What Geneva does is you just specify the UDF. So for example, here's an area UDF. Excuse me. This can be a vectorization UDF or embedding UDF, things like that. You just define that, and it automatically performs that backfilling, or like it performs, adds that column, calculates that, and adds that column across your data set. So you don't have to worry about, if you have a million rows, then calculating this feature for each one of them manually. You can just do that, and it automatically expands across your system. So if you have, the capacity to spin up to like 100 GPUs, it will run across 100 GPUs automatically, and it will do the job for you. So this is how you build something like this. But now coming back to our artwork search example, um, here's one pathway. Now, what I want to stress here is, like, if you have flexible representation of data, you will have dynamic search pathways at every step, right? So I don't know what steps my search or retrieval system is going to take. So for example, this is how it looks in a very simplified format. So I had a lot of sources. I extract some features. I've only listed 4 here, and I get some more features out of those features. So it's like a composite feature. And LanceDB obviously is disk based. So the idea is that LanceDB can um, double down as not only your vector store, but also your object store, and it scales on storage. So, you don't really run out of memory that quickly. So I store all my images and vectors in one place so I can retrieve them from like one server at the same time. And then once this is done, in search time, this is one of the pathways, right? So again, semantic routing in action is happening here. So user inputs something, user can input a text, user can input an image, user can input text and an image. I don't know that. So if this is a particular branch, I extract some mood keywords. I caption if they have the image. I rewrite the query to incorporate maximum context. Then I will say, okay, which feature is the most relevant for this? So it could be vector feature, it could be a full text search feature, it could be an image feature. All right. In the next step, then again, I have to make a choice whether I need to pre-filter or not. Okay, then if I pre-filter, I still have a choice what type of search to use. I know the feature that I'm going to use, but it could be hybrid search, it could be vector search, it could be full text search, right? And then if I'm done with that, should I re-rank or should I not re-rank this data? It's fine. Then there's another choice. All of these things, all of these decisions are being made dynamically. So you sort of have this living and breathing system that improves over time, right? So this is a semantic routing in action. So I'll show you a quick demo. This is something that is work in progress, and we've not deployed it like on larger servers. But what we built was, we built this sort of application to search artwork. And what I did was I asked LLMs to sort of I asked LLMs, all the common ones, Claude, ChatGPT, and Gemini, to describe their favorite artworks, right? Like it does not have to be specific, in both poetic and literal sense, just to see if this particular tool was performing well, right? So it was kind of my way of vibe evaluating stuff, and I'll show you some results, right? So one of the artworks, I've written down some of the prompts that Gemini gave me. Um, so this was the prompt. Like I told it to describe any artwork of your choice as a poetic description of the emotion it evokes. Don't make it too long. You can describe it as a poem or a prose, right? And then for literal, I just told it describe the same artwork in a literal sense. So I'm not asking it to provide me any particular kind of artwork. So if I just paste it here, oh, I'll just have the results here. So if I paste this here, this is sort of the artistic description of a very common, a very famous artwork called Persistence of Memory, and this is what it gives me. If you look at the prompt, it always just describes the emotion, not the exact artwork, because as you can see, like the brown cliffs melt, meet a still vast sea, and then it talks about all of those things, and then sort of the barren branch and metal sheet and things like that. And I get all of these. But not only this particular artwork, it also gives me other things that might evoke similar meaning. So it gives me this composite artwork or something that is built on top, something that's inspired by this artwork, right? So this is a work on top of Persistence of Memory uh, by Salvatore Dali. And then we see some other sort of shores and deserted land and things like that. So you get to see that as well. So this is not really meant for artwork search. That's not the deal, but it still sort of gets the right artwork. The intention was to, this is just for evaluating. The intention was to give you, to sort of find out the artwork that sort of evokes the similar emotion. So it's not meant for searching, but just for evaluation purpose, it actually gets back. What I can do is I can pretty much search the literal sense as well, and I get the same thing or similar things, not the same. So I say the artwork shows multiple clocks melting in a desert-like setting. One of the molten cloth is hanging from a dry stem. Others are lying around. Again, gives me the same thing, and you see there's some differences as well. So you'll see more of derivative artworks from this particular artist. So someone got inspired from this, and maybe they built this, and you can see the results here, all of that, right? uh, and uh, and by the way, you can also like combine with an image. So what I did here was I combined with Van Gogh's Starry Night. Any one of you, like I use the same artistic uh, sort of description and then combined it with this image. So anyone who has worked in neural style transfer, you might know that that is a very famous artwork. And so you see what you expect to see. You see these results where it sort of tries to capture both of them, right? So you see shores and abandoned sort of cliffs and stuff, and then you also see the painting structure, the texture of this oil paint or things like that, and uh, and it sort of continues like that. So it tries to match both of them together. And obviously, uh, this is, we're not looking for a specific artwork. There is no right or wrong here. Like you just see, because we're not looking for one specific artwork, but you try to see the model, sort of the search model intends to find the right artwork that sort of tries to balance both of them. So that is pretty much it. And you see this artwork is exactly that, by the way. This is Salvador Dali's painting, or the derivative artwork of that in Van Gogh style. So that's one of the specific ones, but otherwise it's that. Um, I don't know, we can do something with the Great Wave. This is one of the other very common uh, ones. So I'll just search it here. So I've not kept the server hot. So the first few searches take more than 3 or 4 seconds, or if I have not kept it warm, it will take maybe more than that. But it starts to sort of fill up with not just that particular painting which we're looking for, or I mean the prompt describes, uh, but again, similar to that, you see a bunch of others that have the same, that evoke the same emotion, right? So this is again a famous one, but it's not exactly Van Gogh's. These are derivative artworks to that and all of that, right? So that's the idea. And then you can just search with the image directly, not even any text. So you're walking across, you come up with some, you look at some intriguing artwork, you can just search for that, and that's fine. it will find if something like that exists in the real world, right? Okay. So that's semantic.art. We might be launching it soon. Right now, it's not launched on a dedicated cluster. So first few searches will take time and then it will warm up. But yeah, it's just a demo of this working system of um, semantic routing or dynamically choosing the search path. Anyway, so that's that. Cool. Yeah, that brings me to the end of this talk. I'm happy to answer questions now if anybody has them. I'll see the chat window now. Okay. Um, okay. How systems evaluate the documents are relevant. So there are different metrics for that. Generally, it's hit rate or recall. So hit rate is in your data set. Data set looks something like this, where there's one column with prompts or the queries, and the other column is the correct context. So when you evaluate that, you ingest all the context in a vector database, and then you at particular top k or top 5 in this case, you retrieve 5 at the same time, and then you match if the correct context is in that 5. If it's there, then it's a positive hit rate. If it's not there, then it's negative. And then let's say you had 100 queries, you got only 50 hit rates uh, on all the prompts, then your hit rate is 50%, and that's your evaluation metric. In hybrid search, is there a fixed ratio of different search techniques, or this is dynamically determined? I will try to answer this question, but I would like to confirm if the person is here. So I have one clarification question I'd like to ask. If not, I'll just answer based on what I understood. Looks like they're not here. Oh, I'm thinking, Namrata, you're here. I have a question for you. What do you mean by the fixed ratio of search techniques? Could you elaborate more so that I understand the question? Um, okay, so I was not able to hear you. Maybe it's a problem with your mic, but I'll try to answer that question the way I understood. So when I said it's a mixture of sparse and dense, maybe you're asking, which has more weightage. The answer is it really, yeah. So the answer is that it really depends on the re-ranker. So what happens is both of the search techniques give me, let's say if I'm setting top K at 5, so I get 5 results from full text search or BM25. I get 5 from semantic search, and then what I get is two search can or list of two results. What I do is I combine them using a re-ranker. So I just append them and then I re-rank using one of the re-ranking techniques that you set. And then when I do that, uh, the results are mixed and they are re-ranked. And then I give you the top 5, top K. So it really depends on the type of re-ranking techniques you use, which one has more weightage. Yeah, it's not specific to that. Okay, no worries, no worries. Um, all right. Okay, yeah, I think that is pretty much it. If anyone has any other questions, feel free to ask. Just turn on your mics, or if you'd like to ask them in written format, just post it here. Okay, I don't think there are any other questions. All right.
Okay, I see that there are no questions. Does anyone have more questions? You can ask Ayush right now. That would be great, actually. Or you can even drop in chat. That's fine. We're going to wait for a couple more minutes, and if not, then we just end the workshop. Okay, I think there are no questions. Okay, so thank you so much, Ayush, for such a good workshop, and thanks everybody for joining in. Just make sure to leave a quick feedback for the workshop, and thank you so much, Ayush, for your time and for such great slides. And that's all. Thank you so much, everybody.
Thank
See you
you.
all.
Thanks for having me.
Thank you. Bye bye.
Bye.
Bye bye.